this is the competition from the weaving side to the well-known technology in knitting. They can do seamless knitting, and Dr. Baha Rafat is the knitting father in Egypt, and I'm going to show him how we can compete using woven fabric technology. And I believe that the innovation in this area could lead to reduction in labor cost due to seamless fabric. You don't have to do cut and sew, or you can reduce the cut and sew dramatically. You know the adverse consequences of cutting and sewing. It's labor intensive, which is not suitable for countries like European countries and US, and in the future is not going to be suitable for other countries. Maybe Egypt is one of them. We know that when you use needle, you can damage the fabric sometimes, especially when the fabric is tight. You can damage the fabric and cause holes. High-tech fabrics, for example, holes could cause problem. Let us take example as protective clothing. In protective clothing, you have certain tightness in the fabric. If you have holes, you're going to have weak points that the material can go through and hurt the body. So you have to avoid needle holes. You have concentration and stresses. When you have seams, the seams cause problems. Even the needle holes combined with the concentration of the stresses can cause premature failure of the product and cause problems for the user. Human error are involved in cut and sew. We use human. And seam create bulkiness that sometimes cause discomfort for the user. And fabric waste from cut and sew, because the fabric is produced in straight, width is the same, so you have to cut and sew to get the shape. There are attempts in the literature that we found, and we found several attempts to try to do shapes on woven fabrics. And you can see the figure on the left, this one here, is showing you how we can shape the woven fabric. In this research here, and you can see the source at the bottom, in this research here, what they do to make shape is to get on the left here and the right and take some yarns and make them not woven, rub them from the weaving process. So you can take the shape, as you see, you can see the shape coming with different widths. That's what you need in shape. And with this here, this is what you can get here, a shape like this, and you can produce these shapes using this technology here, or this method. You can produce shapes like this. But if you look at this problem, this method here, these threads here are going to stay in the product after weaving. So you have to do manual work to cut them. You have to cut them out. So you have a scissor, and you start cutting these. It's manual work also. So despite that we have the shape, you still have manual work after the weaving process, which is again labor intensive. We have some problem removed, but some problem exists. And also you cannot weave from a beam. Having some threads not woven at the edges will cause you to make the feed for these yarns from different sources like packages. You have to put creel behind the loom to feed these yarns. Because if you don't, the length of these yarns are going to be slack from the beam. If you have them from the same beam, you're going to have slack yarns and you're going to stop the loom. You cannot weave without having different equipment. So you have additional equipment, plus you still have to do manual work to cut the extra threads. Shaped fabric are important in blood vessels. What you see here is the ascending aorta replacement. This here is a woven tube, and the surgeon got to shape it. It's straight tube. And I'm going to tell you about the problems associated with straight tubes in medical textiles. This here is straight tube, and to fit the valve, the surgeon got to cut. The surgeon became a tailor. He got to cut and sew during the process of surgery, and this takes time. The other problem associated with straight tube is the valve. This is what you see. This is a heart valve. You have 3 leaves. Those 3 leaves, 1, 2, 3. These 3 leaves open to let the blood flow, and the closes. Open and close. When you open, they form this hole here. When they close, you close the valve. These 3 leaves have bulges. They go outside the tube. And these bulges is not here. In real aorta, you have these spaces. When these leaves open, it rests in the space without hitting the space. But in here, these leaves hit the wall of the tube, which make the leaves, which is part of the body, part of the heart, an important part, makes these leaves wear down quickly. And you have to replace now another part in the heart valve quickly. If you would like to design this the right way, this is the right way to design. That's the exact shape of the ascending aorta. This is what you see here. And this is a replacement done by Fabricard. He is a mechanical engineer, biomechanical engineer, or biomedical engineer, who developed this, and he proved mathematically the blood flow will be right if you create exact shape like the human aorta. If you don't, you get problems. God created this way and got to be this way. So he did this. Again, he using here cut and sew. A lot of work need to be done. And all what I said about cut and sew here are valid. All the problems arise. And this is sensitive part. And this is the way we put it in the heart. A company, this company here, Vascotech, is medical textile company, and they said this shape here is the right shape or better than the straight tube. You need a straight tube, and then you need here a skirt, and you need another color here. So you need to, they make bulge for the leaves of the heart valve to get inside it without hitting it. And this here is easy to make. But again, what they did, they make seams. They still do the seams. And all what I said about seams are valid again. Problems associated with seams are well known, and I don't need to repeat. This is seamless airbag. This is a United States patent. Sorry, it's a Japanese patent, but they take US patent in 1998. And what they do here, you have here double cloth. The problem with the airbag seams, the bag fails when you need it. It fails. It fails from where? From the seams. The seams break and make the bag useless. So it causes really dangerous situation for the driver and passengers when you need it. So this here is what you see here at the circle area is double cloth. Double cloth, woven double cloth is well-known technology since ages ago. And we can do double cloth very easy in any loom. The double cloth here you have 2 layers, unstitched. And around it, around the circle, you have 1 layer woven fabric. Woven stitches, not needle stitches, which is much stronger than needle stitches. Needle stitches, you have 1 yarn going around, but here you have many yarns. All the warp yarns and filigree yarns contribute in the seam, and they make strong seams. So you have better bag, and this actually is in the market since several years ago. This is the summary of the problems with previous work. And when we start doing our research, we looked at this previous work and look at the deficiencies in this previous work. You have limited production speed because of the manual work required. It's expensive and needs specialized loom or equipment. And it still requires manual operation, as I mentioned. So our new objective here, our new research objective, is to form shaped seamless woven products by strategically placing construction parameter with different construction parameters, such as different weave in the same fabric, different thread density, the ends per inch, picks per inch, or per centimeter. And we use filling yarn with different shrinkage. The idea here is to build in the fabric, to build differential shrinkage between different parts to get the shape. And the other objective is to study the influence of woven fabric structure or construction parameters on the filling shrinkage, so I can design fabric or design shape before I weave. And we're going to talk about this. We've done 3 sets of experiments. One of them is in Muller. Muller is shuttle loom with width in reed 4.4 centimeter, which is suitable for medical textile like the aorta and blood vessels. And here is the particulars about the warp density. Big density was variable in this case because I want a different shrinkage. And the warp yarn was the same, 70. We didn't change anything in the warp. Same warp yarns all over from the edge to edge. And the filling yarn, we have 200 denier high shrinkage yarn, polyester, and 70 denier low shrink yarn, which again textured polyester. So the whole thing is polyester. And we did weave 3 different weaves: plain weave, 2x2 twill, 3x1 twill, and 2x2 basket, 4 weaves. We use also shuttle weaving loom, which is a little wider, 25 centimeter, about so, and you have again here these particulars about the warp density and peak density. But we have high shrinkage yarn and low shrinkage yarn, and we use this with different blend. Warp yarn, here filling yarn, we have 560 denier high shrinkage yarn and 600 denier low shrinkage yarn. And we did weave 2 weaves, 4x4 twill and 4x4 basket. We done also on wide loom, shuttleless loom. It doesn't have to be shuttle. You can use shuttle loom also, shuttleless loom. And these are particulars about the shuttle loom. Shuttleless loom, we used low shrink and high shrink yarns, ultra low shrink yarn. So we have 3 types of filling yarns here: low shrinkage, very low, and very high shrinkage yarns. We use double cloth again here in this loop. The high shrinkage yarn, or one of them, was the type 400 elastomeric yarn. This yarn here, when you look at it before weaving, before finishing, it looks like any textured yarn. So it's easy to weave. After you weave it, you can finish it at certain temperature. When you finish it, it develops the elasticity just like lycra. It becomes lycra after finishing, not before. Lycra is very difficult to weave, especially when you put it in warp and filling. This is the finishing procedures. So the strategy here is to weave, and you'll get the fabric off the loom just like any fabric, same width everywhere, straight edges. And once you finish it, the shape develops. Here is the shape. This looks like the ascending aorta done by the Visitech company. Same. I don't have any seam here. And what we did here, we have 3 portions here, this end here, and this end here. We call this end 1. These 2 ends here, we call them end 1. And the one in the middle, we call end 2. Sorry, end 1 is the top, end 2 here, and they are similar. And the middle end, or the middle portion, is done by this weave. So we can see here what we've done in end 1 and the end 2 are the same. And if you look at it, we encourage shrinkage. We have more shrinkage here than here. To encourage shrinkage, you need loose weave. That's loose weave. To discourage shrinkage, you have tight weave, plain weave. And once you get this straight tube, and once you finish it, you develop high shrinkage here, low shrinkage here, you get the shape. We've done this, the difference between the middle dimensions and the end dimension is 21%. So we played with these parameters to change this percentage. And you can see here we've done 3 samples, extra 3 samples with different setting. If you look at, this is sample 2, sample 3, sample 4, and this is 2, 3, 4, sample 1 was the previous one. And you can see here with different, you can have different shapes. And different shapes are good here because you need to fit different ascending aorta. Everyone has different dimensions. So we can tailor for every patient, we can tailor an ascending aorta. More here the same, we have the highest shrinkage were accomplished by sample 6, 43%. And we can do more, we can do even more percentage. I have some samples here I will show you at the end. If you are interested, you can come closer and see it. These are the samples. If you have both sides, you can see from there. You can see the middle portion, because I mentioned the end. And I can make 2 ascending aorta here by stopping here. Okay. And I have all the samples that I showed you, all of them right. This is not only good for medical design, it's good for even apparel. This is what we've done on the 25-inch loom, or 25 centimeter loom. And what you see here, we have 100% here high shrinkage yarn at this portion. High shrinkage yarn after finishing is going to shrink more. So we have less dimension here. This is tube. And then we have 0 shrinkage, high shrinkage yarn. We discourage shrinkage. And when you have this extreme side by side, you get bulge, you get curvature. And then we can do gradual decrease to do conical shape, like you see in the leg of a pant and sleeve of a jacket or shirt. You have here big bar going gradually smaller. And you can see here how we did this. We have here 33% high shrinkage, which means that we did 1 peak high shrinkage and 2 peaks low shrinkage. And here 50-50, which means we've done 1 peak high shrinkage, 1 peak low shrinkage. And you can see here, as you increase the high shrinkage yarn, you get higher shrinkage. So you can do the gradual shape. This is straight conical shape. We don't have bulge in this case. And here is the fabric with the bulge, high shrinkage here, low shrinkage here, you get that shape. Okay. This is 2-layer tube. And this is another sample from the high bulge. I didn't bring the sample which has straight conical shape. I think I'll do this. This is a straight shape. Okay? I can put it in the hand, here, or here, right? If you look at a band is big tube here and two tubes here. I can make a band on this tube by using this technology, on this method. I can get a band out of the tube without any button flow. You may need the button flow at the ends. So we minimize the flow in the seam. That's the idea. In the Bicanol, which is a wide shuttleless loom, we've done some study between shrinkage and the tightness of the fabric. I don't want to go through this mathematics. You can read the paper. We use geometrical analysis to correlate the shrinkage with the filling shrinkage, fabric shrinkage and filling shrinkage. So you can design fabric. You want a certain dimension. Once you know the shrinkage, you can calculate the dimensions. If you have these correlations, you can design. And this is the idea behind the study on the Bicanol. Is merely we didn't produce shape. All what we did is to correlate the tightness of the fabric in terms of filling yarn, density, big density, warp density, weave, all the construction parameters that you can imagine. We correlated those to the filling shrinkage, to the fabric shrinkage, so we can design before you decide. I want a shape with these dimensions at the waist. I want a shape at the end, these certain dimensions, so we can get this before you weave. And once you strategically put these parameters in the fabric, you get the shape. So this is what we've done here. You know, I don't want to really take more time. This part here is showing the on-loom tightness, which is something that we all can calculate. And if you want a fabric tightness same, you can go horizontally and get same fabric tightness with different shrinkage. Why we need same tightness with different shrinkage? I get the shape and I get the same tightness everywhere in the fabric. It's well known that if you have same tightness on the fabric, you can have same properties or approximately same properties. So if you're designing for properties, you can do as well. You can produce the shape and get the property you're looking for. Okay. In the 70s or 60s or even 80s, you couldn't do this, because to change a big density, you have to stop the loom and change a gear, the big gear. How many weavers do we have here? Weavers. One weaver, 2, 3. Okay. You remember in the past, we still have these looms in our plants, everywhere, even in USA. We have looms that you have to change the gears to change the big density. Not anymore. The technologies you need to get these shapes are here today. Variable big density. You pre-program the loom before you weave to do different big densities on the same fabric. You need variable weaving speed. If you have different filling yarn, which you do here in case of shape, producing shape, you can do variable speed for every filling yarn. In the past, what did we do? If we have 3 filling yarns and one of them will break at certain speed, you have to reduce the speed. And you have to go with the minimum speed to accommodate the weakest filling yarn. Today, you can change the speed. You go low, you go high, and using the same fabric without stopping. Automatic filling selection. Since I have filling yarn, this is done by shuttle also in the past. But in the shuttle we have limitations in terms of the number of shuttles. But today you can have 12. The maximum today is 12 filling yarn that you can change. And you can program them before you weave. And I'm going to show you here a short movie showing you how we change the filling yarns. I'm going to make this bigger so you can see it. This here is shuttleless loom with about 8 picks, 8 filling yarns, and you can see here you have different filling yarns, different thickness, different novelty yarns. You can also do 2 picks at the same time, and you can see that there. With the shuttle, how you could do that? You couldn't do with the shuttle 2 shuttles at the same time. You have to do shuttle after another, which reduces the productivity. Today you can do 2 picks, 3 picks, 4 picks, up to 4 picks. Here is 2 picks picked at the same time. And they may need this to get the shape.
5 دقائق يا دكتور. 5 دقائق.
فاضل دقيقتين بس. To change the weave, in the past we had to stop the loop to change the weave. But if I want a shape and I want to change the weave to get the shape, you can do it today by the automatic pattern change. Whether you do pattern or you do simple weave, you can program this on the machine and the pattern can change without stopping the loop. You will see now the change of the pattern without stopping the weaving process. Now it happened. And this technology is there since 1995. Okay. These technologies are becoming the standard, and the old looms that we use today, anything 90 and before, considered old technology because you don't have these new technologies. And I think this will not be options. This will be standard in near future. I have here some other idea I didn't do, but it's ready to be done. This is seamless pillowcase, and this is commodity product. Today, if you understand this research, you can do this in your loom. A simple loom can do it. Shuttle loom can do it. Shuttle-less also can do it. You can see here traditionally some of the pillow has to have hems, and we do hemming. You just take the pillow and fold it and seam it from the 2 sides, you leave it open from here, and you fold it again and make a seam to have a hem. And traditionally this is acceptable, but you can change the design if you want to. You don't have to have the hem, but if you want to have the hem, you can do that. This here is double cloth, unstitched double cloth, 2 layers of fabric. This here is 4 layers of fabric in this section. 4 layers of fabric. Okay. And you can make a pillow and separation between pillows, so you can cut here and you get your pillow ready to be used, just wash and use. This is very simple figure. This is a skirt, and I can shape this skirt. You weave it, finish it, it's ready with couple of seams, one here and one here. Look at this skirt here. If you want to do skirt like that today, how many seams you're going to have? At every line here, we have a seam. And depending on the size, the number of seams increases or reduces. And this is commodity fabric. I'm not saying this research will take over everything, but look at these here. Opportunities and the commodity area. And this is the conclusion. I think we showed in this research that we can do shaped fabric without seams or minimum seams. And we can design this fabric to have shrinkage between 5% to 75%. That's what I've done, but you can do more. More is possible. We develop a relationship between the finished fabric and the fabric construction parameters. Finished fabric shrinkage and construction parameters, which would allow a cloth or apparel designer to design before weaving. And then after designing, you can take these parameters and see which parameters could be used to get the shape required. And like I showed, the recent weaving technology will let you do this at a simple, by doing simple programming. This here will eliminate and reduce the traditional seam and reduction of labor cost. This is a big question. Can the recent innovation in weaving and polymer science and research level the labor cost around the world? I believe yes. Thank you.
نشكر الدكتور عبد السلام على المحاضرة القيمة الحقيقة. هو أنا كنت خايف، ما خوفني قال لي هنبطل التريك وهنشتغل نسيج، ولكن يعني أنا شايف كده إنها فكرة ممتازة وهتاخد وقت شوية عبال ما تتنفذ عمليا، فاحنا هنبقى مستريحين بقى، ما اعرفش اللي بعدينا هم اللي هيتعبوا.